can be the Richter scale. Well, in 1935, Charles Richter defined the magnitude of an earthquake to be logarithm of 1 to the base of, with the base of c over 1 to the base of, sorry, I instead of 1, to the base of n equals r. Where IC is well, the upper part of the equation is intensity of the earthquake measured by the amplitude of a seismograph reading taken 100 kilometers from the epicenter of the earthquake, exactly 100 kilometers. If not, this kind of thing cannot take place. And IN is the intensity of a standard earthquake, whose amplitude is 1 micron equals 10 minus 4 centimeters. That's the basic measure you have to compare with. Basically, it is a measure of how much the Earth moved during the earthquake versus how much the Earth moves on a normal day, on the average day, because Earth moves all the time. Another example we can find with this kind of stuff, population is the population growth. When a population has a constant relative growth rate, its size can be calculated using a natural exponential function. The population p after t units of time, p times t equals p times 0 e to the power of kt, where k is a constant relative growth rate and p 0 is the initial population measure at time 0. So you have to make it proportional to the lifespan of the organisms you're analyzing. So for example, for populations of bacteria, this lifespan is going to be shorter, in contrast with an analysis you can make about humans. So in this case, the value of k is negative. Everything else remains the same. Now I'm going to give the word to pass the word to my friend Vicky, who's going to explain a little bit about carbon dating and giving a little conclusion. Thank you.
As Martin said, I'm going to talk about carbon dating. So carbon dating is another example of logarithm, and it's a technique used by scientists to date fossils or other types of old artifacts. It relies on the principle that the C214 isotope of carbon decays. This means that it has a constant relative rate of decay. The same equation is used for the situation as for continuous compounding and population growth. With situations involving decay, the rate of the growth is always negative. The half-life of a substance in the amount of time it takes for half of that substance to decay. It is only a property of substance that decay at the rate proportional mass. Through research, scientists have agreed that the half-life of C214 is approximately 5,700 years. The decay constant K for carbon-14 can be calculated using the half-life. Using the constant relative rate of decay functions, we say that the remaining amount of carbon-14 C to the T equals C times 0 times E to the negative KT. K is negative because C times T decreases as T increases.